Let's go over the pipeline of hypothesis testing that we have been studying. First, clearly state the null hypothesis. Stating the null hypothesis so that it is crystal clear is essential to be able to simulate it. Next, define your test statistic. Then generate many sets of simulated data assuming the null hypothesis is true. Compute the test statistic for each simulated dataset. The p-value is then the fraction of your simulated datasets for which the test statistic is at least as extreme as for the real data. Now let's do another hypothesis test. Consider again Michelson's measurements of the speed of light. Around the same time that Michelson did his experiment, his future collaborator Simon Newcomb also measured the speed of light. Newcomb's measurements had a mean of 299,860 kilometers per second, differing from Michelson's by about 8 kilometers per second. We want to know if there is something fundamentally different about Newcomb's and Michelson's experiments. The thing is, we only have Newcomb's mean and none of his data points. The question is, could Michelson have gotten the dataset he did if the true mean speed of light in his experiments was equal to Newcomb's? So we formally state our hypothesis as this. The true mean speed of light in Michelson's experiments was actually Newcomb's reported mean, which we'll call the Newcomb value. When I say the true mean speed of light is in Michelson's experiments, think the mean Michelson would have gotten had he done his experiment lots and lots and lots and lots of times. Because we are comparing a dataset with a value, a permutation test is not applicable. We need to simulate the situation in which the true mean speed of light in Michelson's experiments is Newcomb's value. To achieve this, we shift Michelson's data such that its mean now matches Newcomb's value. See here the ECDF of the shifted data relative to the original data. We can then use bootstrapping on this shifted data to simulate data acquisition under the null hypothesis. The test statistic is the mean of the bootstrap sample minus Newcomb's value. We write a function diff from Newcomb to compute it and compute the observed test statistic. We then use drawBSReps, the function you already wrote, to generate the bootstrap replicates, which is the value of the test statistic computed from a bootstrap sample. Note that the data we pass into the function are the shifted Michelson measurements, because those are the ones we use to simulate the null hypothesis. The p-value is computed exactly the same way as for the permutation test. We report the fraction of bootstrap replicates that are less than the observed test statistic. In this case, we use less than because the mean from Michelson's experiments was less than Newcomb's value. We get a p-value of 0.16. This suggests that it is quite possible that Newcomb and Michelson did not really have fundamental differences in their measurements. This is an example of a one-sample test, since we had one set of samples from Michelson and we're comparing to a single number from Newcomb. Often in the field, you will do two-sample tests that require the bootstrap, which you will explore in the exercises. I know this video was a lot to take in. Explicitly simulating a null hypothesis like this, where we have to shift the mean, can be tricky. You'll get a chance to practice in the exercises, and you may want to go over the procedure again to make sure you understand it. Okay, enough talk. Let's do some bootstrap hypothesis tests.